Guys, welcome back to Pablo versus YouTube channel where curiosity meets the code. Today we are going to be discussing about supervised machine learning algorithms in detail. So let's get started. So firstly, the agenda for today is giving a clear idea of what is linear regression, logical regression, decision tree, random forest, super vector, machine scale, nearest naive bias, gradient boosting, neural network. So as you know, these are the major algorithms involved in supervised learning. Then, so we have supervised machine learning algorithms. Firstly, going with linear regression, it predicts a continuous variable based on one or more important features. The objective here is to predict the relation between a dependent variable, which is output, and one or more independent variables. This features by lifting a linear equation. The equation here being y is equal to mx plus b, where y is the dependent variable, x is the independent variable, and m is the slope, and b is a y-interpret. The goal here is to minimize the sum of squared differences between the predicted and actual values. Next, we have some of the assumptions. So assume a linear relationship between variables and that the residuals, the difference between the predicted and actual values, are normally distributed. Some of the use cases include commonly used for predicting modeling, understanding relationship between variable, and making prediction based on historical data. And we have evaluation, which performs often assist using matrices like mean squared error, which is MSE, or R squared. So secondly, we have logistic regression. This is used for binary classification task where the goal is to categorize data into two classes. So the type here include linear model for binary or multi-class classification. The output here is log odds of the probability of a particular class. Then we have activation function, which is sigmoid function, maps logs odds to probabilities. The parameters used here are coefficients for each feature and bias terms. Then we have training, which is maximum likelihood estimation to optimize the parameters. Next, we have some of the decision boundary, which is hyperplane separating classes. Some of the regularization include L1 and L2, which is lasso and ridge regularization to prevent overfitting. Then we have interpretability, which is coefficient indicate feature importance. Then some of the use cases are binary and multi-class classificational problems. And the assumption made here is to assume a linear relationship between a feature and log odds. Then we have evaluation, which is metrics include accuracy, precision, recall, and F1 score. Some of the implementation includes widely available in machine learning libraries. Next, we have decision tree, which is the third algorithm, a tree-like model that makes decisions based on input features. The objective here being make decisions or prediction by recursive splitting the data based on feature, creating a tree-like structure. Then we have the structure being the node represented decision points based on features, edge represented possible features, outcomes, and leaves represented the final decision or prediction. Then we have splitting criteria algorithms, which is Gini impurity for classification, mean squared error reduction for regression, determine the best feature to split at on each node. Then we have decision process, which is follow branches of the tree from root to leaf and leaves classes, which is classification or value in the final prediction. Next, we have some of the interpretability, which is of the decision tree, which is highly interpretable, providing insights into important features and decision-making logic. Then we have handling missing values, which can handle missing values well by choosing alternative branches. Then we have n-ensembles method, which is often used in n-ensemble methods like random forest, combining multiple decision trees for improved accuracy and robustness. Then we have pruning. These are techniques like pruning help prevent overfitting by removing branches that do not contribute significantly to the predictive performances. Some of the use cases include versatility for both classification and regression tasks, widely used in various fields due to simplicity and interpretability. And the visualization here is easily visualized, aiding to understand the decision making process. So moving the fourth algorithm here is random forest, which is an ensemble learning method using multiple decision tree. This is a collection of decision tree for improved accuracy and robustness. And for training, we have bagging, which is random sample data with replacement. And then we have random featured selection, which is each tree considered a random subset of the features at the each split. Then we have voting, which is classification, which is majority vote of the predictions averaging for regression. Then what are some of the benefits here? It includes reduced overfitting, robust to outliers, and provides feature importance. So next we have parameters of the so the parameters here includes number of trees, which is n estimators. Then we have depth of the trees, which is maximum depth, minimum sample of splitting, we have minimum sample split, and minimum sample per leaf, which is minimum sample leaf. And some of the use cases here include classification and regression, handle high dimensional data, and we have interpretability, which is less interpretability than single decision tree. Then we have implementation is efficient in popular libraries, examples scikit-learn. Then we have trade-off, which is increased computational cost but offers provide improved performances. Next, the fifth one is support vector. So here's it classifies the data by finding the hyperplane and the best separators classes, which is object, which is find a hyperplane that the best separates data into different classes. Then we have hyperplane, which is decision boundary with the maximum margin from the nearest data point, which is support vector. Then we have kernel trick, which is maps data into higher dimensional space, allowing for non-linear decision boundaries. Then we have margin, which is distance between the hyperplane and the nearest data points, and we have SVM aims to maximize this margin. Then we have C parameter, which is controls the trade-off between achieving a smooth decision boundary and classifying training points correctly. Next, we have some of the kernel functions, which is linear kernels suitable for linear separable data, which is radial basic function RB F kernel, which handles non-linear relationship. Then we have support vectors, which is data points that influence the position and orientation of the hyperplane. Then we have some of the use cases being efficient of binary classification that can be extended to multi-class problems. Then we have sensitivity to outliners as they can impact the position of the hyperplane. Then we have some of the parameters, which is C choice of kernels and kernel specific parameters. Then we have interpretability, less intuitive compared to simpler models like linear regression. Some of the implementation here is in various machine learning libraries such as scikit-learn. Then we have trade-off, which is efficient for high dimensional spaces but may require Turing parameters for optimal performances. Next, we k nearest neighbors, which is classify data points based on majority classes of their neighbors. The algorithm type is instant based or lazy learning algorithms. Principal classifies data into points based on the majority classes of their k nearest neighbors in the feature space. Then we have distance metric, which is commonly used Euclidean distance, but other matrices can be employed. Then we have parameters such as k of the neighbors to consider. Some of the decision process here is for classification, the majority vote of the k neighbors determined the class. Then we have for regression, we have the majority vote of the k neighbors determines the class. Then we have for regression, average for weight average for of the k neighbors values predicts the target. And then we have the scalability, which is computationally expensive for large data sets as it requires calculating distance of each prediction. Then we have feature scaling, which is sensitive to the scale feature, so normalization is often. Next, we have some of the use cases, which is effective for small, medium-sized data sets. It works well when Decision boundaries are complex or non-linear. Then we have decision boundaries, which depends on distribution of data points and can adapt to different shapes. Then we have non-parametric. This does not make strong assumption about underlying data distribution. Implementation such as simple to implement and understand available in popular machine learning libraries. And we have trade-off, which is balance simplicity with potential high computational cost, especially for large data set. Then we have tuning, which is optimal choice for of k and distance metric, depends on nature of the data. Next, we have the Naves bias, which is a classifier, is a probabilistic algorithms based on Bayes theorem and assumption of feature impedance. It's commonly used for text classification tasks, spam detection, sentiment analysis, and documentation categorization. The type here being probabilistic model based on Bayes theorems. Then assumptions here include features are conditional independent given the classes, and we have some of the types here as Gaussian, which is continuous features. Then we have multimonial discrete features, which is Bernoulli's binary features, and training estimated class condition and prior probabilities. Next, we have some of the supervised machine learning algorithms with the prediction of it of Naves bias. Then we have select the class with highest probability of given feature. Some of the use cases here being test classification, spam filtering, high dimensional data, strengths, which is efficient, require small training data effective for high dimensional. Then we have weaknesses such as assumes feature impedance sensitivity to irrelevant features. Then we have evaluation, which is metrics include accuracy, precision, recall, and F1 score. Then we have some of the implementation, which is available in machine learning libraries, easy to implement. And then we have trade-off, which is simplicity and effective efficiency of the naive impedance assumption. So some of the last one we'll be speaking about is gradient boosting. This is an enhanceable learning technique that builds the multiple decision trees sequentially, with each tree correcting the errors made by previously once. Then we have XGBoost, which is light GBM, and other gradient boosting libraries are known for their excellent performance on a wide range of supervised learning tasks, which includes classification and regression. The type here being ensemble methods combining weak models, which is often decision tree, which is objective, which minimizes residual sequential to improve model accuracy. Then we have some of the algorithms, which is fit weak model, which calculate the negative gradient of loss. Then we have fit the new model to negative gradient, update the model with weight contribution, then repeat until the specified number of models. Next, we have the shrinkage, which controls the contribution of each weak model and prevents overfitting. Then we have regularization, which controls the tree depth and number of trees to prevent the overfitting. Some of the use cases here are regression and classification tasks. Some of the advantages here is handles mixed data types, robust of outliners, provide features important. Some of the weaknesses here can be computationally expensive, requires hyperparameter tuning, and evaluation here includes metrics like mean, squared error, and accuracy. And we have implementation available in libraries, which is XGBoost, Light BGM. Then we have some of the trade-off, which includes powerful but requires careful tuning and can be resource intensive. So ninth one in the last one includes neural networks. Have this has gained a popularity in recent years, mainly due to their effectiveness in tasks like image and speech recognition, natural language processing, and autonomous driving. They consist of interconnected layers of artificial neurons that can approximate complex nonlinear function. The type here is deep learning model inspired by the brain's neural structure. Then we have architecture, which is layers of interconnected nodes with weights and activation function. Then we have training, which is propagation, adjust weights based on error between predicted and actual outputs. Then we have the types here is feed forward network, which is FNN. Then we have recurrent, which is RNN. Then we have convolution neural network, which is CNN. Then we have the deep learning, multiple hidden layers for learning hierarchical representation. Then we have some of the use cases here as image recognition, speech processing, various machine learning tasks. Advantages here includes learn complex patterns, effective for large data sets, which challenges required is significantly computational resources, which is sensitive to hyperparameters. Then we have evaluation dependence on the task examples, accuracy, precision, and recall. Then we have implementation, which is supported by framework like TensorFlow, PyTorch. And lastly, we have the trade-off, which is a powerful for complex tasks but demands resources and careful thinking, tuning. So that's it for today. Thank you so much for watching. If you have learned something from this video, please do like, share, and subscribe to our channel. Thank you.